Hello and welcome. This is going to be our lecture video for the Unit 8 test review on solutions. Let's go ahead and get started with the multiple choice. So I'll just go through these quickly so you can just check and see if you got them right. Substance being dissolved is known as the solute. Which of the following would make a solid dissolve faster? Just shaking. Sometimes we call that agitating. A concentrated solution is one in which there is a large amount of solute and a small amount of solvent. The solubility of a dissolved gas will blank if the temperature of the liquid containing the gas decreases. So it's going to just follow the temperature and also decrease. That's just a direct relationship. If more solvent is added to the solution, the molarity is going to decrease. That's option A. So we're dividing up the same amount of solute into a bigger and bigger volume. So that decreases the concentration, and concentration is measured in molarity. All right, in number 6, in general, as the temperature of a solvent increases, the solubility is also going to increase, which means the amount of solid dissolved is going to increase. Number 7, maximum amount of a substance that dissolves in a given quantity of a solvent, that is the solubility. Solubility is how much will dissolve in a given amount of water. Volume is measured in liters. Which of the following is a common solvent? H2O is our most common solvent, sometimes called the universal solvent. What are the correct units for concentration? Well, we normally say molarity, but molarity is moles per liter, so we'll pick option B there. Number 11, a dilute solution has less solute per amount of solvent than a concentrated solution, so that's option A. Point at which can no longer hold more solute, that is saturated. And then next one is supersaturated. If something is supersaturated on a solubility curve, it will be above the line. And then to turn a supersaturated solution into an unsaturated solution, you just increase the temperature is one of many ways. You could do it in several ways. You could add more solvent, but that's not one of our options. You could somehow decrease the amount of solute. That's not one of our options. And then by increasing the temperature, you're just increasing the solubility, so our solution can hold more. All right, on to our short answer. So number 1 asks us to determine the molar mass of the following compounds. To do that, you need your periodic table, and you just need to add up all of the parts of the molecule. So for the first one, I need to add 1 calcium and 1 oxygen. In the next one, I need to add 1 carbon plus 4 times the molar mass of hydrogen, and so on. I'll do all 4. All right, so I added them all up. You can see them there. Notice the unit for each of these is grams per mole. All right, number 2, convert the following. How many grams are in 3.25 moles of sodium chloride? So I'll start by writing what the problem gives me. 3.25 moles of NaCl. I'll put that on the top of a unit conversion bar. And now I need to multiply by a conversion factor that converts what 1 mole of NaCl weighs in grams. And to figure out what 1 mole of NaCl weighs, I need to add up its molar mass from my periodic table. And I get 58.44 grams of NaCl per 1 mole of NaCl. Now just multiply that by the 3.25, and I get 189.93. Just grams now, so 189.93 grams of sodium chloride in 3.25 moles. Next one, going the other direction. So I've got 87 grams of CO2, and I need to convert back to moles. So here, I got to figure out what 1 mole of CO2 weighs, but I'll put that on the top because I want grams to cancel out. Now I add up 1 carbon plus 2 oxygens. 44.009 grams of CO2. So what I actually end up doing is doing 87 divided by 44.009. To get that in 87 grams of CO2, I would have 1.98 moles of CO2. All right, number 3. So we've got a molarity problem. So molarity equals moles divided by liters. The solution has 3.4 moles, and it's being dissolved in 1.5 liters. So 3.4 moles divided by 1.5 liters. Gives us a concentration or molarity of 2.27 molar. All right, next one asks it in a kind of different direction. What would be the volume of the solution if you have 0.489 moles of lithium fluoride and want to make a 2 molar solution? So again, molarity equals moles over liters, but we know that the molarity is 2. We have 0.489 moles, and we're just trying to figure out how many liters it's dissolved in. So I multiply the liters to both sides, divide both sides by 2 to rearrange this to be liters equals 0.489 divided by 2, which equals 0.245 liters. All right, on to the next one. So now I know the liters and the molarity. I just got to figure out, well, how many grams, but to do that, I have to figure out how many moles first. So molarity, 4.5 equals moles divided by liters, 0.75. Multiply both sides by 0.75, and I get 4.5 times 0.75 is 3.375 moles. But how many grams? So I got to multiply by how many grams 1 mole of calcium chloride weighs. And calcium chloride, I add up. It's got 2 chlorines. So I can multiply the mass of chlorine by 2. Get 110.978 grams per 1 mole. Multiply like this, and moles will cancel out. So times 3.375, I get 374.55 grams. Of calcium chloride. All right, another one kind of like that. We got to do moles over liters, but we first have to convert grams to moles. So 16 grams of iron chloride. It's going to be how many moles? So add up the iron. The chlorine, I get, that's 126.745 grams per 1 mole. And I get that I have about 0.126 moles of iron chloride. And now I can just divide that by how many liters I have to turn it into liters, move the decimal place 3 times. And I get a molarity of about 0.505 molar. All right, and on to number 7. Now we're on to a dilution problem. So we want to make 250 milliliters of a 2.5 molar solution. That's kind of where we're ending up. So I recognize this is an M1 V1 equals M2 V2 problem. And I know that my final molarity is 2.5, so I'll fill it in for M2. And the final volume is 250, so I'll fill that in for V2. I have a 10 molar stock solution, so I'll fill that in for M1. And the only thing I don't know is V1, but I can solve for it now. 10 times V1 equals 2.5 times 250 is 625. If I divide both sides by 10, get that V1 equals 62.5. And because we put our volume in as milliliters, this is also milliliters. So 62.5 milliliters of the stock solution diluted up to 250 milliliters gives us the desired concentration. All right, number 8. Final concentration of a solution if you start with 1.5 liters of 12 molar stock solution. So I can fill that into M1V1 equals M2V2 right away. I have the stock solution is a molarity of 12, and I have 1.5 liters. Now I'm trying to find the final concentration, so I don't know M2, but I add 3 liters of water. Well, 1.5 liters plus 3 waters means I'm going to have 4.5 liters. And now I can just solve for M2. So I'll do this in my calculator. 12 times 1.5 equals 18. Divided by 4.5 equals 4. So the final molarity is 4 molar. All right, and then the next one is similar. So I've got 25 milliliters times 18 molars sulfuric acid is going to equal 300 milliliters times what? So 25 times 18 divided by 300 gives me 1.5 molar. All right, number 10, use the graph to answer the following questions. Which compound is most soluble at 40 degrees? So I'm going to go to 40 degrees and start coming up, and I see that at 40 degrees, our beaker holding 100 milliliters of water could hold almost 90 grams of NaNO3. So NaNO3, it's the highest number, so it's the most soluble. Which compound is supersaturated at if 50 grams of the solute is dissolved in 100 milliliters of water, and the temperature is brought to 20, so I'm going to go up from 20 until I get to the 50 grams, and I'll make a point right here. Well, right here at this point, I'm above both the KNO3 and the NaCl, so I've saturated that solution of both KNO3 and NaCl. All right, which would be unsaturated with 100 grams if we're at 80 degrees. So I'll go up from 80 and make a point at 100 and see that both the NaNO3 and the KNO3 are unsaturated. because I'm below those lines. So KNO3 and NaNO3. All right, at what temperature does potassium nitrate have a solubility of 87? So I'll estimate about where 87 is and come across to my potassium nitrate. I think it's going to hit right about there. So I'll say approximately 40 degrees Celsius. All right, if you have 100 grams of NaNO3 at 60 degrees, so NaNO3, 60 degrees, 100 grams of it, so we're right there on the graph. And allow the temperature to decrease. What temperature will crystals begin to form? So as I decrease down, well, I'm already below. So, oh, sorry, I'm going to move this way until I hit the graph. And at that point, I'm at my saturation point, so the crystals will start to come out. So it looks like I hit right there at about 50 degrees. At 50 degrees is where the NaNO3 would be saturated. And anything below that would be supersaturated, and we would precipitate out crystals of our NaNO3. All right, how much more potassium nitrate will it take to saturate a solution that currently holds 25 grams at 40 degrees Celsius? So we're at 40 degrees Celsius. We've already put in 25 grams, but to get up to the saturation point for potassium nitrate, which looks to be maybe about at 60, we need to add in about 35 more grams to get from here up to here, which is the saturation point. Okay, another one. A solution contains 75 grams of sodium nitrate dissolved in 100 milliliters of water at 30 degrees. Would it be considered saturated, unsaturated, or supersaturated? So 100 milliliters at 30 degrees. We're at this point right here. Well, we're above the line, so it would be considered supersaturated. Supersaturated. All right, number 11, 11A, would sodium chloride be soluble? So we have to look for the parts of this ionic compound in our table here, and we see it actually has two. It is an alkali metal, because sodium is in group 1, which is the alkali metals, and it is a chloride, so it's double soluble. So would sodium chloride be soluble? Yes. How about magnesium hydroxide? So magnesium's not alkali, it's in group 2. And then hydroxide, I see over here, on the insoluble side. So since there's nothing in the soluble side and something in the insoluble side, we'll say no, not soluble. Now, NaHBr, well, I see bromide, so that's over here, but the NaH is also ammonium, so two things from the soluble category. This would be highly soluble. All right, and we've got a question about Beer's law. So we construct this graph very similar to how we did our Beer's law. If an unknown concentration absorbs 30 relative units, what's its concentration? We're just going to draw a line coming over from the 30 until we hit our graph, and then we'll go straight down to find the concentration. And I see 0.6. This says relative, but it was supposed to really be molarity. So it's probably 0.6 molar solution. All right. And then part B kind of clarifies that. If the x-axis is molarity and a sample contains 0.8 molar solution, how much would you expect the sample to absorb? So I'll go to the 0.8 and now go straight up until I hit my line, and then go straight over to the graph, and I would see 40 units is where we hit. All right, and that's that for this lecture video. Good luck studying. Have a good rest of your day.